Okay, in this video, we're going to talk about cosmic microwave background radiation in the Big Bang and some cosmology. So we're going to talk about cosmology. Now, the idea is in the Big Bang is that you've got the universe started at a singular point, and that point is obviously what exploded outwards with all matter in it, and that formed eventually into galaxies and solar systems and everything else out that we know today, and creating the universe as we know it. Now, the point is that there's a lot of things in cosmology, there's a lot of evidence to suggest what's going on here, and you've got a situation where when these were given off, obviously this was a very, very hot, singular point, okay, very dense and very hot, singular point at which all matter was gathered in and then exploded outwards. And obviously, like I said, creating the galaxies. Now, the evidence for this is that as these galaxies shot off, they were obviously giving off light, and every galaxy that is traveling away from this singular point, so these are all galaxies, by the way, are traveling off, and as a result of that, they are giving off light, and there was light given off during the Big Bang. Now, obviously, you can imagine from a Big Bang, you'd have an extremely high amount of energy. So you might think something in the form of gamma rays are given off, very high frequency, high energy waves. Now, obviously, because over the billions of years that this has happened, 14 billion to be the approximate value that's taken now from the Hubble constant, these waves will spread out, and when this galaxy reaches, say, this distance right here, then by that time that radiation will have spread out. Now, obviously this is a form of redshift, so it's been shifted towards the red end of the spectrum, and what you might end up getting over a long period of time is, instead of gamma, you might end up getting microwaves, because these waves have spread out so much over the years that they have spread out to the point where they are now microwaves instead of gamma rays. And so the issue here is that we can actually have a look at these waves and make some observations about them, and we actually call these microwave radiation that we see nowadays cosmic microwave background radiation. And that cosmic microwave background radiation is often shortened to CMBR, for short. And you can use that abbreviation should you wish. So CMBR, cosmic microwave background radiation. Now the thing is that on Earth, when we're on Earth, what we are seeing when we look out in every direction, we're seeing this cosmic microwave background radiation. And so because we see that in every direction, it's giving us a little bit of a clue that at one point in the universe's history, that maybe, just maybe, there was a much shorter wavelength kicking around. And because all of this radiation is everywhere, spread out, it gives us an indication that, and because of the spreading out nature of the universe, the fact that the universe is expanding means that this is being redshifted. So that's a really key point we should note down. So this shifted radiation is evidence of an expanding universe, which we see around us all the time. Now, there are a few kind of pieces of terminology that can go with this explanation. The fact that the universe is what considered to be isotropic and homogeneous. So isotropic and homogeneous are very similar kind of terminologies. So the idea that homogeneous means the universe is the same in every location, whereas isotropic means it's the same in every direction. Now, you don't need to worry too much about that, but we call that the cosmological principle. And for all intents and purposes, as long as you can accept this terminology, then you won't go far wrong. So when you're talking about the evidence for the Big Bang, we're talking about the Big Bang was a hot, dense, singular point in which all matter exploded outwards. Obviously, the fact that it was hot and high energy means that it gave off high energy waves, just like gamma. And so as a result, over time, the expanding universe that we observe because of all this redshifted radiation, the CMBR that we see around us all the time, we can assume that the radiation from the Big Bang has redshifted over time. And that goes along with the idea that we see redshifted spectra coming from the galaxies that are moving out from a singular point. And the fact that everything is moving outwards makes it suggest that everything is moving out from a singular point. Now, there are some interesting kind of calculations you can do around this. Now, the universe at the moment, because of that cosmic microwave background radiation, we can actually predict that the universe has a temperature of about 2.7 Kelvin. 2.7 Kelvin. And the interesting thing about that is that prediction is based on the fact that we treat the CMBR as black body radiation. So black body radiation obviously follows that principle where you've got a certain high intensity proportion wavelength, and that's known as the peak wavelength. Now, what's interesting about that is that we can use Wien's law. Now, you might remember Wien's law from previous videos, being that lambda max is equal to Wien's constant, which is 2.9 times 10 to the minus 3, divided by the temperature in Kelvin. And oftentimes, the fact that we treat CMBR as black body radiation, that there's a specific temperature associated with it. Now, what's interesting is that this matches our predictions of the Big Bang and the fact that we treat the CMBR as black body radiation. Now, we can also use this idea to predict how hot the universe was when, say, for example, the light was, instead of being in the radio waves, which we're talking about, meters and centimeters long, we can actually then say, well, how hot was the universe when the radiation that was emitted was, say, let's pick a number, so 700 nanometers, just as an example. So 700 nanometers, if the wavelength was 700 nanometers when at a certain point in history, then we can say, well, lambda max, which in this case, our max wavelength we're seeing of the highest intensity is 700 nanometers, we can use Wien's law to actually work out what the temperature of the universe was when the background radiation was of this peak intensity. So lambda max equals 2.9 times 10 to the minus 3 over the temperature. So the temperature is 2.9 times 10 to the minus 3 over the lambda max, which in this case is 700 times 10 to the minus 9. And when we work that out on a calculator, so 2.9, this is me working it out on a calculator now. That gives us a temperature of around 4,000 degrees Kelvin. Obviously I get an answer of 4,142, but never is going to be that accurate anyway. But the fact that we can use Wien's law to actually show that, yes, it was very hot when it was longer ago, and that makes sense, that follows our judgments there, that actually the radiation we're seeing, if we actually measure the temperature of the universe out and about now, it actually is that temperature. So the fact that we're treating this radiation as blackbody radiation, we're following Wien's law, the temperature that we predict it to be, 2.7, matches what we see today. And so this is a really useful thing. So don't forget about the key facts that I've kind of outlined on this sheet over here. Go back, have a look through your notes or your textbook, and just look at the key principles there. But for the most part, I've got them all here. The fact that the hot dense singular point, redshifted radiation, creates cosmic microwave background radiation because it was redshifted, because that means there was an expanding universe. And because what happens is the universe is isotropic and homogeneous in every direction, basically it's the same in every direction, then we can assume that these rules and this all follows through for the whole universe, and that it all comes from this Big Bang. So have a look through that. If you have any questions when you come to lesson, do let me know.